Measurement accuracy can easily be enhanced by accessing the new SIM, or signal integrity modeling, which allows you to de-embed transmission line effects, view virtual test points when probing close to the device under test is not practical, or simulate extra components to better reflect the real world, effectively performing a simulation of your design under different conditions. Here we have an eye diagram of a high-speed serial signal on channel 1 after it has passed through 6.75 inches of printed circuit board trace. We can clearly see the parasitic effects of the signal path on the transmitted signal and how it has caused the eye to close. We can apply de-embedding to remove these channel effects and view the signal at the device transmitter, even if we can't access it directly. Simply tap Add New SIM to start building a new model. SIM allows you to quickly visualize changes to the signal path using both a physical and simulated circuit model. Physical model represents all physical components to be de-embedded in the signal path that was used to acquire waveforms. The simulation model enables what-if exploration, showing how the waveform would look when an alternate circuit is embedded. For example, in the physical model, we can represent the PCB trace and the 1-meter cable as part of the measured signal path. But in the simulation model, these effects are completely removed and replaced by an ideal load. SIM introduces simplified workflows that start with only the essential blocks and lets you add more as needed, saving time and reducing complexity by keeping setup focused on the task at hand. For more demanding scenarios, the advanced workflow enables combinations of methods within a single simulation. For this scenario, I simply want to remove the effects of the PCB trace and the cable, so I will choose to use the simple de-embed workflow. I will select two-port system analysis since we are using a single cable. If we were modeling a differential signal path, we would choose 4-port analysis. This workflow starts with a single block in the physical model that is configured as a through by default. I will use this block to represent the 1-meter cable by double tapping to open it for configuration. I change the model to S parameters and ensure the type is set to 2-port. I click the Browse button to locate and select the S parameter file that represents my cable. Finally, I rename the block so I can easily keep track of it in the block diagram. Next, I need to model the PCB trace. I do this by clicking the Add Block button and then drag the block into my model, placing it where it exists in the real physical system, between the cable and the device transmitter. I will configure the block and change the model to S parameters. The S parameters for my PCB trace are 4-port, so I will change the type to 4-port and then select the file. In this system, I'm only using 2 ports, but my S parameters are 4-port. I can choose which 2 ports I want to use by selecting them from the block port dropdowns, eliminating any need to edit the S parameter files to remap the ports. I can quickly plot the S parameters to verify that my block configuration is correct. I see the expected transmission loss profile in the S12 plot, so I know that these S parameters and my selected ports are good. Finally, I'll rename the block for tracking purposes. In the simple de-embed workflow, the de-embed test point has already been added for us in the simulation model. It is represented by the green dot that sits between the device transmitter and the ideal load. No additional configuration is needed here. Now that my model is built, I will tap Calculate Sim to compile the model and create the de-embed test point filter. Tap OK to go back to the scope waveform view. We can see a math waveform representing the waveform at the de-embed test point has been added at the bottom of the display. We can create an eye height measurement for the new Math 1 waveform and plot an eye diagram. By de-embedding the PCB trace and the 1-meter cable, we can see the open eye at the device transmitter without any signal losses. Comparing the eye height measurements, we can see that the signal lost over 170 millivolts of eye height due to impairments caused by the signal path. Unlike legacy tools, which limit you to one simulation at a time, now you can compare practically an unlimited number of circuit models simultaneously. Each one outputs to a math waveform and can be daisy-chained for complex what-if modeling scenarios. Pairing SIM with jitter analysis enables comparing multiple eye diagrams and measurements simultaneously and without compromise. Tektronix tools are uniquely designed to enable simple analysis when complexity is low, and advanced analysis, where multiple sources and measurement configurations can be analyzed simultaneously, saving significant test time.